Welcome to G Fun Facts Online. For thousands of years, we've tried to guess the weather. From old sayings about red skies at night to the first barometers, it's been a constant battle against the atmosphere's chaos. The 20th century gave us supercomputers and a physics-based approach called numerical weather prediction, or NWP. It was a huge leap, trying to capture the weather using mathematical equations. And it worked, getting better decade by decade. But it was always a slow, expensive race against an unpredictable force. Now we're on the edge of an even bigger revolution. A new kind of forecaster has arrived, one that doesn't use physics equations, but the power of pattern recognition. Artificial intelligence is here, and it's starting to beat the old methods in both speed and accuracy. This isn't just a small step forward, it's a complete paradigm shift that could change our relationship with the weather forever. But as we start to trust these powerful new AI tools, we also have to ask, what does it mean to truly understand the chaos we're trying to tame? The idea that you could calculate the weather isn't new. It started over a century ago with a Norwegian physicist named Wilhelm Bjerknes. In 1904, he proposed that weather forecasting was basically a math problem. If you knew the current state of the atmosphere, the temperature, pressure, wind, you could use the laws of physics to calculate its future state. He dreamed of a rational, scientific way to predict weather, a clockwork sky. But his dream was way ahead of its time. The equations were so complex that solving them by hand was impossible in any useful time frame. The person who truly understood the scale of this challenge was a British mathematician named Lewis Fry Richardson. During World War I, while serving in an ambulance unit, he decided to try and calculate a 6-hour weather forecast for a single spot in Europe. It took him 6 weeks, using just a slide rule and logarithm tables. The result was a spectacular failure, predicting a bizarrely huge change in air pressure. But the experience gave him a profound insight. In his 1922 book, he described his vision for a forecast factory. He imagined a giant circular hall with a map of the world on its walls. He calculated that you would need 64,000 human computers, each working on one piece of the puzzle, all directed by a central conductor, just to keep up with the real-time weather. It seemed like a fantasy, but it laid the groundwork for what was to come. The real breakthrough came after World War II with the invention of the first electronic computers. The brilliant mathematician John von Neumann, who helped develop the ENIAC computer, saw that weather prediction was the perfect job for these new machines. In 1948, he put together a team of meteorologists in Princeton. They simplified the physics equations and, in April 1950, used the ENIAC to produce the world's first computerized weather forecast. The ENIAC was a monster. It filled a 30 by 50-foot room and had nearly 18,000 vacuum tubes that broke down constantly. It took them over 24 hours to compute a 24-hour forecast. The forecast itself wasn't great, but it proved Richardson's vision was possible. This was the birth of numerical weather prediction, or NWP. So how do these traditional models actually work? At its core, NWP treats the atmosphere like a giant fluid, governed by fundamental laws of physics. These are expressed in a set of complex equations that track the conservation of key quantities. One equation tracks momentum, which is basically Newton's second law, applied to a parcel of air. It describes how winds are affected by pressure, the Earth's rotation, and friction. Another tracks energy, governing how air temperature changes from solar heating, cooling, and the release of heat when clouds form. Other equations ensure that mass and water are conserved, and the ideal gas law ties pressure, density, and temperature together. To solve these equations, the model first divides the entire globe and the atmosphere into a three-dimensional grid. Each cell in this grid can be several kilometers wide. The model is then fed an initial state, a snapshot of the current weather, compiled from a massive network of weather stations, balloons, aircraft, buoys, and satellites. This process is called data assimilation. Once the supercomputer has this starting point, It begins to calculate how the variables in each grid cell will change over a short time step, maybe a few minutes. The result becomes the new current state, and the process repeats, stepping the forecast forward in time, hour by hour. But this physics-based approach has always faced huge challenges. First, the computational cost is astronomical. It requires some of the most powerful supercomputers on Earth, which consume enormous amounts of energy. A single 10-day forecast can take hours to run, making it a luxury not all countries can afford. Second, there's the problem of resolution. Even in the best models, the grid cells are too large to capture small-scale weather like individual thunderstorms or turbulence over a mountain. To handle this, modelers use a technique called parametrization, which uses simplified formulas to approximate the effects of these smaller processes. It's a necessary simplification, but also a major source of error. Finally, and most importantly, NWP is limited by the chaotic nature of the atmosphere itself. This is the famous butterfly effect, discovered by meteorologist Edward Lorenz. Tiny, unnoticeable errors in the initial weather data can grow exponentially over time, eventually making the forecast useless. Because our observations are never perfect, there's a fundamental limit to predictability, usually around 10 to 14 days. For 70 years, progress has meant building bigger computers and better observation networks. But now, a radically different method has arrived. Instead of solving physics equations, the new generation of AI weather models learns the weather directly from data. They are trained on decades of historical weather archives, learning the incredibly complex patterns of how the atmosphere evolves. It's like teaching a child to recognize a cat. You don't give them a textbook definition, you just show them thousands of pictures of cats until their brain figures it out. AI models are shown decades of past weather maps until they learn how one atmospheric state leads to the next. At the heart of this revolution are different types of neural networks. Some, like Google DeepMind's GraphCast, represent the Earth as a network of connected points, learning how conditions at one point influence its neighbors. Others, like Huawei's Pangu Weather, use transformer models, the same technology behind language models like ChatGPT, to analyze weather data like a sequence of words, capturing long-range connections across the globe. All of these powerful AIs are fueled by one critical ingredient, a dataset called ERA5. Produced by the European Weather Center, ERA5 is a reanalysis dataset. It combines historical observations with a top-tier physics model to fill in any gaps, creating a complete, consistent, gridded history of the global atmosphere stretching back to the 1940s. It's the gold standard historical record that these AIs need to learn from. This data-driven approach has two game-changing advantages. The first is speed. Once an AI model is trained, it can generate a 10-day forecast in under a minute on a single specialized processor. That's orders of magnitude faster than a supercomputer that takes hours. The second is efficiency. The energy needed for an AI forecast can be thousands of times less than a traditional one. This could democratize weather forecasting, allowing smaller organizations to run high-quality models on a laptop. The true test, of course, is how these models perform in the real world, especially during extreme weather. In September 2023, as Hurricane Lee churned in the Atlantic, Google's GraphCast model accurately predicted its landfall in Nova Scotia, a full 9 days in advance. Traditional models only converged on that same prediction about 6 days out. That 3-day improvement in lead time is invaluable for emergency preparedness. The year before, during the devastating Hurricane Ian, another AI model called WeatherMesh predicted its landfall location 200 kilometers more accurately than official forecasts at a 70-hour lead time. And during Super Typhoon Saola in Asia, Huawei's Pangu weather model suggested a more accurate track near Hong Kong earlier than its conventional counterparts. But despite these impressive successes, there's a major hurdle: the black box problem. With a traditional physics model, forecasters can trace an error back to a specific equation or assumption. With a deep neural network, the decision-making process is often opaque. It's hard to know why I made a certain prediction. This is a critical issue. If an AI predicts a hurricane will suddenly intensify, a forecaster needs to know if it's picking up on a real atmospheric signal or if it's just an error from a quirk in its training data. The risk is especially high for what are called gray swan events, extreme weather that is unprecedented and lies outside the historical data the AI was trained on. Since AI is a pattern recognition system, it struggles to predict something it has never seen before. A University of Chicago study showed this perfectly. They trained an AI on a dataset that excluded hurricanes stronger than Category 2. When tested, that AI consistently failed to predict the formation of a Category 5 hurricane. In the real world, that kind of mistake could be catastrophic. To solve this, a field called explainable AI is emerging. The goal is to peek inside the black box. Techniques like salience maps can create heat maps that show which parts of the initial weather data the model paid most attention to. This allows a meteorologist to see what the AI is looking at and judge if it makes physical sense. The future of forecasting isn't about AI replacing the old methods, but about creating a new, hybrid era. The most promising path is to merge physics-based models with data-driven AI. For example, AI can be used to replace the computationally expensive and error-prone parameterization schemes in traditional models, learning to approximate things like cloud formation more accurately and efficiently. Another approach is using a fast global AI model to produce a large-scale forecast, and then feeding that into a high-resolution regional physics model to simulate local details, like winds whipping through a mountain pass. This combines the speed of AI with the detailed physics of NWP where it matters most. The ultimate goal might be a fully AI-driven system. A project at the University of Cambridge called Aardvark Weather aims to replace the entire forecasting pipeline with a single AI model. It can ingest raw observational data and output a global forecast in minutes on a standard desktop computer. If successful, this could truly democratize weather prediction, giving any organization the power of a supercomputer. This AI revolution also extends to the even bigger challenge of climate modeling. Simulating the climate over decades is incredibly demanding. But AI emulators can run climate simulations thousands of times faster than traditional models, allowing scientists to generate huge numbers of possible future scenarios to better understand the risks of global warming. The integration of AI into atmospheric science is just beginning. For now, AI models still rely on the physics-based models for their training data, so the two are linked. And they still struggle with some key variables, like telling the difference between rain and snow. The future isn't about machines replacing humans. It's about augmentation. I will handle the heavy lifting of data processing, freeing up human forecasters to focus on what they do best: interpreting the outputs, understanding the risks, and communicating life-saving information to the public. We've come a long way from Richardson's fantasy of a 64,000-person forecast factory. The new weathermen have arrived, and they are made of silicon and data, giving us a powerful new tool in our ancient quest to understand the beautiful, chaotic dance of the Earth's atmosphere.